Yeah, it started.
It started, right? Okay. Okay, great. I will transfer the host privilege to Professor Sugisaki. Okay, that is done. Or shall I make Professor Sugisaki the co-host and give host to Dibo? Maybe that would be better, right? Because then Dibo can control the YouTube live streaming controls.
Yeah, yeah. No
Okay,
problem.
okay. Professor Sugisaki, I'll just make this one change.
Yeah.
Okay, thank you. So I've made Professor Sugisaki the co-host. And then I'll make Dibo the host. Okay. Okay. Professor Sugisaki, can you check if you're able to share the screen?
Okay. Shall I see my slide?
Yes, we are able to see it on Zoom. We'll just check if it's also visible on YouTube. Yes, we are able to see your slides on YouTube.
Yes, yes.
Yes, we are able to see your slides on YouTube. Yeah, the audio is also fine. Okay, then maybe we can begin in the next 3 minutes or so. Okay, I'll go mute till then. Okay, so then maybe I'll begin by just giving a very brief introduction.
Yes.
Okay. So good morning to everyone. Today we have Professor Sugisaki giving his second lecture in the lecture series Quantum Chemistry on Quantum Computers. In the previous lecture, he spoke on general introduction of quantum computers. Today, he'll be discussing with us on quantum algorithms, in particular teleportation, Deutsch-Jozsa, quantum fingerprinting, quantum Fourier transforms, and so on. So yeah, Professor Sugisaki, thank you.
Thank you very much for kind introduction. and welcome to the second lecture of the quantum chemistry on quantum computers. And today I'm going to talk about the quantum algorithm and the focus how the quantum computers will perform some particular problem algorithm. In the previous lecture, I introduced this slide. The quantum computation begins with basically it consists of the three steps. First is initialization of the quantum state, and then perform some quantum operation. And then finally measure the quantum state to read out the results. So the quantum operation depends on the algorithm you want to simulate. So actually, in the previous lecture, I introduced this quantum circuit, which consists of two Agamal gates and two CNOT gates and one CNOT gate. And actually, this quantum circuit is designed to perform the summation of two one-bit integers. I mean, these two above top two qubits are for input, and these bottom qubits are for the output. And these Agamal gates are introduced to state preparation, and this CNOT gate can perform the summation of cubic integers. And the quantum state before the measurement was calculated to be shown here. It becomes a superposition of 0, 0, 0, 0, and 0, 1, 0, 1, 1, 0, 0, 1, and 1, 1, 1, 0. Actually, as you can see, the former qubit in red is input, and the blue ones are output. So it means, actually, that if we perform this quantum circuit, we can obtain the 0 plus 0 equals 0, 0 in binary, and 0 plus 1 equals 0, 1 in binary, and 1 plus 0 equals 0, 1, and 1 plus 1 equals 1, 0 in binary. So 1, 0 means 2 in decimal. So this is one of the typical example of the quantum operation to perform some particular problem. And before discussing the data of the quantum algorithm, I would like to introduce excellent website, quantum algorithm Q, named as quantum algorithm Q, and URL is shown here. As you can see, this website summarizes many quantum algorithms reported so far. You can see that, for example, factorization is the speed up is for polynomial. It means that exponential in classical computer actually and to the something like this to the power of the order n1/3 on classical computer, but it becomes a polynomial scaling on quantum computers. And also there are many references included in this website, so you can find the quantum algorithm and some brief introduction of the algorithm. And first, I want to discuss about quantum teleportation. But before discussing quantum teleportation, I would like to introduce very important theorem. I mean the no-cloning theorem. The no-cloning theorem is reported in 1982. It says that unknown quantum state cannot be cloned by unit operation. So the process is something like this. Let's imagine that there is a unit operator that can clone the quantum state. So if we starting from the quantum state phi, their product of phi and zero state, and then apply a unit operator u, it can generate the phi and phi, the product of phi and phi. And also, if we apply this unit operator to psi, it can also generate a psi times psi. Let's imagine that we have a quantum superposition space alpha, which can be written as the linear combination of phi and psi, as shown here. And the question is phi and psi. If we apply the unit operator that can from the quantum state, we can derive this equation. Applying U operator to the alpha state, and alpha state can be decomposed as a phi 0 plus psi 0 state. So application of the U operator can be calculated. And the action of the U operator can be calculated as shown here. And also, let us think about the application of U directly to alpha. It can generate the alpha times alpha state. And if we expand this alpha state by using phi and psi, we can obtain this equation. And clearly, equation 1 and equation 2 contradict to each other. So it means that unit operator that can copy a non-quantum state is impossible. However, a non-quantum state cannot be cloned, but it can be teleported by using a quantum teleportation. In order to discuss the quantum teleportation, let's think about the two people, I mean Alice and Bob. Alice has a non-quantum state, phi, which can be a linear combination also on one state. Alice wants to send this unknown quantum state to Bob. In order to perform this quantum teleportation, we need entangled state, entangled two qubits. And quantum teleportation starts by sending this entangled qubit to Alice and Bob. And Alice performs signal and agamma operation. The quantum state can be calculated as shown here. The original state is the direct product of the quantum state phi and the entangled state. And this quantum state can be expanding like shown here. And first, Alice performed the signal gate as the qubit Alice wants to send as a control and the qubit of the entangled one as a target state. The quantum state can be calculated as shown here, applying knock operation. If the control, I mean the first qubit, is one state, so 000 becomes 000, and 011 also becomes 011, but 100 state becomes 110, and 111 state becomes 101 state, and then perform the agamma operation. The quantum state is transformed to like this equation, and we can rewrite this equation as shown here. As you can see, these first two qubits, I mean the 00 or 01 or 10 or 11 states, are the quantum states Alice has, of the two qubits Alice has. And this quantum state in the called parentheses is the quantum state of the qubit Bob has. And if the Alice measures two qubit states, these two qubits, if the outcome of the measurement was 11 state, the quantum state of the qubit Bob has will project it to this function state. So by measuring the two qubits, Alex measuring the two qubits, the measuring outcome becomes 1 or 0 or 1 or 1 2 or 1 state. And by measuring the quantum state of the both qubits will project it to the quantum state as shown here. And the final step is the classical communication between Alex and Bob to tell the measurement outcome to Bob. And if the measurement outcome was social state, and the quantum state of the Bob qubit is shown here, and original quantum state Alex want to send was shown here. So if the measurement outcome is one social state, the quantum state of both qubits is already the unknown quantum state Alex want to send to Bob. So if the measurement outcome was social state, we have nothing to do to recover the original state. But if the measurement outcome is 0-1 state, for example, the quantum state of both qubits is shown here. And in order to recover the original quantum state, Bob has to perform a NOT operation by applying a Pauli X gate to change the 1 state to 0 state and 0 state to 1 state to recover the original quantum state. Again, if the measurement outcome was 1 0 state, the quantum state of the both qubits is shown here. And as you can see, only the phase is different between the original quantum state and the quantum state shown here. So in order to recover the original quantum state, both have to perform and has to apply a Pauli gate to change the phase from minus to plus to recover the original state. So quantum teleportation needs a three-step contains the three steps, signal, and argument, and measurement. But quantum teleportation needs the classical communication between Alex and Bob. So the speed of the information transfer does not exceed the speed of light because it contains the classical communication. Next, I want to introduce the Deutsch-Jozsa algorithm. Deutsch-Jozsa algorithm assumes that there are n blocks in the can distinguish the quantum state is either pure or mixed state. Assuming that there are n balls in the box, so here, the box are either all red or all blue. This corresponds to the pure state, or half red and half blue, or mixed. It means a mixed state. So, how many trials do you need to identify either pure or mixed state? Let us think about the case of n equal 8. So we have 8 balls in the box. If you are lucky, you can specify the quantum state is mixed one by the 2 trials. For example, the first you can put you can obtain the blue ball, and the second step you obtain the red ball. So it means the balls are mixed. But in the worst case, you need 5 trials to specify or identify either pure or mixed state. So basically, if the number of balls is x, unique, in the worst case, unique x divided by 2 plus 1 trial to identify either pure or a mixed case. But if you can use the Deutsch-Jozsa algorithm on quantum computer, the same can be improved. And in order to discuss the Deutsch-Jozsa algorithm, we have to introduce a black box. Let us assume n equals 8 in the previous slide, and red is equal, black is 0 and blue is 1. The system can be, for example, 001, 011, 001, for example, for the mixed case. So for pure case, the system can be 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1 case. And black box needs a 3-bit binary input, such as 011 or 101 or 000, and then return the x value of this system. So it means that if the input is 000, 000, it returns 0 as the output. And if the input is 100, it returns 1 as the output. This is a black box for classical computer. And let us think about the black box for quantum computer. Because quantum computers, all of the operation except for the measurement should be unitary. So we need the same number of input and output strings. So in this case, we need 4 qubits. 3 of the qubits are for input, and 1 is for output. And quantum black box allows quantum superposition as an input. And it returns the starting from the input state and output qubit should be inside the 0 state. And then perform this black box operation, it returns the output state in the output qubit. So the initial quantum state is, for example, 011 state, 0110 state. Shown here. The output state is also 0110 state. But input is 0100 state, the output should be 0101 state. And the quantum study for the Deutsch-Jozsa algorithm is shown here for n equal 8 cases. It consists of the 6 agamma gates and 2 black boxes and 1 Pauli gate. And let us calculate the action of this quantum study. The original, the starting at the beginning, the quantum state is inside to the 000 state. And first, we perform the 3 agamma gates to generate the superposition of these 8 basis states. And then perform a black box operation. It returns the quantum state as shown here, and red and the beacon in red specify the output state. After that, we perform a Pauli operation to the left qubit, which will change the sign if the output qubit is 1 state. And after that, again, we perform a black box operation to generate the quantum state as shown here, and then perform a 3 agamma gate. The final quantum state is shown here. So if we measure these 3 qubits, at least one of the qubit measured outcome should be 1 state. If the system is pure state, the final state is 0, 0, 0, 0. So if the system is pure state, all the qubit measurement becomes 0 state. So you can distinguish either pure or mixed by using this quantum study. And let us think about the scaling of the Deutsch-Jozsa algorithm. Assume small n equal 2 to the nth power. So n equal 8 means that large n equals 3 means that small n equal 8. On classical computers, we need 2 to the n minus 1 power plus 1 operation to specify either pure or mixed case in the worst case. But on the quantum computer, we need 2n plus 3 operation to specify the pure or mixed case. So the same becomes something like this. If n equals small, for example, 3, the number of operations is larger for quantum computer. I mean, the classical computer needs at most 8 operations, but the quantum computer needs 9 operations to specify the pure or mixed case. But if n increases, the number of operations on classical computer will increase exponentially, as shown here. But the number of required operations on quantum computer is just a polynomial theorem, as shown here. So this Deutsch algorithm is very efficient if the n equals very large. Next, I would like to introduce the SWAT test. The SWAT test was introduced in the paper on the quantum fingerprinting. In the classical fingerprinting, the fingerprint cannot be made exponentially smaller than the original thing unless the party preparing the fingerprint to have access to the correlated line of sources. But in the quantum fingerprinting, the fingerprint can be exponentially smaller than the original string. And in this quantum fingerprinting, the SWAT test is introduced as a key process. And SWAT test calculates the overlap between 2 quantum states, let's say phi and psi. And the quantum study for SWAT test is very simple. Just it includes one atom gate, and then perform control SWAT operation, and then another atom gate, and measure the quantum state of the unshaded qubits. And let us calculate the action of the quantum study. The original state is so phi psi. And first, we apply an atom gate to the unshaded qubit, which generates the superposition of 0 and 1, and then perform control SWAT operation. So control SWAT operation do nothing if the control qubit is 0 state, but it swaps 2 quantum states if the control qubit is in 1 state. So the quantum state after the control SWAT operation is calculated like this, and then perform another atom operation. The result is shown here. And we can rewrite this equation like this. And if we measure the quantum state of the top qubit, the probability to obtain the 0 state in the measurement is calculated like this. So the probability is proportional to the square overlap between two quantum states. So let us check the here I want to demonstrate the test on IBM-Q. I will do actual simulation right now. You can connect the IBM quantum computer. If you already have a IBM ID, you can log in this page. First, run compose. Let's generate a new file. This untitled circuit includes 3 quantum bits, 3 qubits, and 3 crystal bits. And the sub operation is composed of these 3 operations. So let's generate the quantum circuit. First, apply a gamma gate, and then control swap operation. But the control swap operation can be generated in QIST, I mean the IBM quantum computer, by first introduce a swap operation, and then introduce the control theory, like this. And then include another gamma gate. And finally, we need the measurement of the quantum state. And in this case, the Q1 and Q2 correspond to phi and psi. And in this case, the Q1 and Q2 are the same quantum state. So we can naturally expect that the outcome of the probability of obtaining the zero state is unity, because in this case, these phi and psi are the same quantum state. So 1 plus 1 divided by 2. So the probability becomes 1 state, 1. And let us check by performing the simulation. So doing simulation can be done by clicking this side. And first, we perform the quantum circuit simulation using a schedule vector simulator. Let's run the simulation. We already obtained the result of the simulation. As we expected, the final state is only the 000 state. So 100% we can obtain the 0 state in this quantum circuit. But if we introduce some phase shift to the for example, first qubit by introducing RY gate, and if we introduce the RY with the rotation angle pi over 2, thus, and then perform the same simulation. It's running. Now we can obtain the different probability to obtain the 0 state and 1 state. If we perform the same quantum circuit with the rotation angle Ry theta equal pi, in this case, the rotation of pi rotation changes the 0 state to 1 state, so that we can obtain the almost equal probability to obtain the 0 state and 1 state. And this is a result of the state vector simulator. And they perform the same quantum circuit using a real quantum computer. So I just removed the RY gate. So expected the outcome of the measurement is always the state. And let us perform the same this quantum circuit by using, let's say, for example, IBM-Q manual. It takes a few seconds or a minute. Now the job is sent to the IBM-Q manual. Now the job is impending. Well, it is now the job is in queue, but the expecting to run in 2 minutes, so I will return a few minutes later. The result I perform is something like this. The state vector, the result arises from the state vector simulator is something like this. It's just a very good cosine curve, cosine square curve. But if we use the real quantum computer, IBM-Q manual, the outcome was something like this. So there are some deviations, especially the theta because it's very small. So why such large deviation can be observed? It's because the implementation of control clock gate is very demanding. I mean, the original quantum circuit needs say 1 qubit gate, 2 gamma and RY gate, and 1 control clock operation gate. But transpiled quantum circuit needs 22 1 qubit gate and 15 single gate. Implementation of this control clock gate requires many quantum gates. So that's why the outcome is very noisy. But if you want to calculate the square overlap between 2 1 qubit, you can also use this quantum circuit. It contains just 1 single gate and atom gate. And let us think about the initial state is something like this. The original state is written shown here. And then we perform a single. So this state, for convenience, we can calculate the 305, 305 to 300, and 305, 315 to 301, and so on. And if we apply a single gate, the quantum state is transformed to this. Another atom gate can transform the quantum state as shown here. So the quantum state before the measuring can be written as shown here. Okay, so if we measure these 2 qubits, the outcome should be can be 0, 0 or 1 or 1, 0 or 1, 1 state with a probability proportional to the E square of the equation. The probability can be calculated as shown here. And the original we want to calculate the square overlap between phi and psi, which can be calculated as shown here. And by using these four equations, we can derive that the square overlap between phi and psi can be calculated at by using these four probabilities as shown here. Actually, if we perform the square overlap estimation by using this quantum circuit, the result is very good compared to the original Schwarz test. I mean, this Hong-Ou-Mandel test effect-based approach gave smaller errors, and also the shape of this function is very smooth. Actually, what the difference is the number of quantum gain after transpiration. As I said before, original Schwarz test needs 37 quantum gains to implement on real quantum devices. But in this case, we need only 8 quantum gains even after transpiration. So the number of quantum gains is substantially smaller in this case. So that's why the error becomes very small. And finally, I would like to introduce quantum Fourier transformation. Fourier transformation is frequently used in chemistry, also in other physics or science. The discrete Fourier transformation can transform some function yk to the another form. So it can be the time domain data to frequency domain data. And this is an example of Fourier transformation. This is the experiment of results that was obtained from the ergo experiment using this pulse sequence. The ergo experiment can by performing the ergo experiment, we can explain and determine the distance between 2 ampere electrons. If we perform Fourier transformation, we can obtain this kind of probability density corresponding to the distance of the ampere electrons. So, quantum Fourier transformation is also the same as the discrete Fourier transformation. I mean, the discrete Fourier transformation is defined in this expression, and quantum Fourier transformation is also defined like this. This U is the operator that performs the quantum Fourier transformation. Applying U operator to some quantum state, let's say J state, it can generate the quantum superposition of this kind of quantum superposition with different J and K. For convenience, we write the state J using a binary representation, as shown here. Or also, we use a binary fraction like this. So, if we let us calculate the action of the unitary operator U, the result, this state can be expanding as shown here. So if in case n equal 1, the application of U results in this state. So if J1 equals 0, I mean the j equals 0. In this case, application of u will generate the superposition of 0 and 1, and the phase on the of the one state is calculated as 1. So the final quantum state is just a positive superposition, linear combination of 0 and 1 state. But if j equals 1, the phase is calculated as shown here, minus 1. So application of u to the one state will generate the quantum superposition of 0 minus 1. Actually, this one cubic quantum Fourier transformation can be realized by using the one Agamal gate. Application of Agamal gate to 0 state will generate the quantum superposition of 0 plus 1. Application of the Agamal gate to the one state will generate 0 minus 1 state. In case of n equals 2, this equation can be expanded as shown here. If the j equals 0, the final quantum state obtained by the quantum Fourier transformation is just a linear combination of 0 and 1 and 1 and 1 1. If we apply a U operator to 1 state, the final quantum state is shown here. It's also the linear combination of 0 and 1 and 1 and 1 state, but the phase is different. Again, if we perform the quantum Fourier transformation to 1 state, we can obtain this quantum state. And also, application of U to the 1 state will give the quantum state as shown here. And the phase is something like that. If so, the phase is always in the direction of the real axis. But if we apply a unit operator to 1 state, the phase of the 0 and 1, 1 state will rotate according, in this case, 90 degrees. Application of 1 state, unit operator to 1 state will result in the 180 degree rotation of the phase, starting from this state, 180 degree rotation for 1 state, another 180 degree rotation. So it means that 360 degree rotation from the original state in the 1 state, and so on. And this quantum Fourier transformation can be realized by using this quantum circuit. We need Agamal gate and control rotational gate. And the rotational gate is defined as shown here. This is the phase rotation gate with the phase exponential 2 pi I over 2 to the kth power. And then addition Agamal gate. For n equals 3 cases, we have 8 possibility of the input j. Rotation angle of the phase is calculated as shown here. So this value, so 1, 2, 3, 4, 5, 6, 7, correspond to the binary representation of this quantum state. So means that 0, 1 in binary is 1. 1, 0 in binary is 2 in decimal, and so on. And the quantum circuit for the quantum Fourier transformation for n equals 3 is shown here. It needs the Agama gate and good control location gate, fixed location gate, and another Agama gate, and one control location gate, and final another Agama gate. For general N, the quantum circuit for the quantum Fourier conformation is constructed as shown here. It needs some Agama gate and control location gate, Agama gate and control location gate, and so on. By applying this quantum circuit, we can perform the quantum Fourier transformation. And the application of quantum Fourier transformation is very wide. Actually, for example, the Schwarz algorithm for prime factorization includes the quantum Fourier transformation. Importantly, quantum phase estimation for the eigenproblem of unit operator, which can be used in quantum chemistry to calculate the Fourier energy or Caxial energy. The quantum phase estimation is based on the inverse quantum Fourier transformation. I will discuss in the next video in detail, but in the quantum phase estimation, we first generate the quantum state, something like this, right-hand side of the equation, and then perform the inverse quantum Fourier transformation, which can generate the J state. And then if we measure the J, this quantum state, we can obtain the information on J, which corresponds to the eigenphases of the unit operator, which corresponds to the eigenvalue of the time evolution operator. And also, hidden subspace subgroup problem can be solved by applying a quantum Fourier transformation. Another important application of the quantum Fourier transformation is the solving the linear system of equations, which was proposed by Harrow, Haskell, and Roy. This algorithm, also known as the HHL algorithm. And this HHL algorithm is frequently used in the quantum machine learning problem. So in the next week, I will demonstrate how quantum phase estimation can be performed by using quantum Fourier transformation in detail. This is the final slide of today's talk. I'm very happy to accept your questions. Thank you very much.
Thank you very much, Professor Sugisaki, for your very nice lecture. There are some questions, so I'll just read out the questions.
Okay.
Okay. So Nishant asks, what are the possible real-life applications of the Deutsch-Jozsa algorithm, or can it be used as a part of any bigger algorithm?
Well, application on Deutsch-Jozsa algorithm. Actually, the Deutsch-Jozsa algorithm is one of the quantum algorithms first proposed one. And actually, if you want to perform the Deutsch-Jozsa algorithm, you need to realize the black box operation. So to return the output. But if you realize the Deutsch-Jozsa algorithm, but anyway, the Deutsch-Jozsa algorithm just specify the quantum state is in the input is either pure or mixed one. I mean, the pure means in this case the 000 or 111. A mixed means the I mean the sorry, the pure means if this black box returns always one state or zero state, regardless of the function state of the input. Or in the mixed case, is that it returns one or zero in the 50-50. So, frankly speaking, I don't know what kind of application can be possible by using this Deutsch-Jozsa algorithm. But occasionally, this Deutsch-Jozsa algorithm is very important because, of course, this is the first example of the quantum circuit that quantum algorithm that can accelerate, that allows to perform exponential speed up against the classical counterpart.
Okay, thank you for the answer. Dibajyoti has a question. I'll just read his question. He asks, how does one approach constructing a quantum circuit, like general guidelines, once they know the problem and the method to solve?
So the question is about the construction of the quantum circuit.
Yeah, I think he's asking for whether there are any general guidelines given a problem and our approach to solve the problem. Are there any general guidelines that one adopts to construct?
Okay. So, construction of the quantum circuit is, of course, depends what kind of problem you want to solve. So basically, that depends on the algorithm. In order to perform the quantum simulation on using the quantum circuit, I mean, let's say the IBM-Q or some quantum state simulator, you need to decompose the quantum operation U to the some set of the basic quantum gate, such as Adamo, rotational gate, power gate, and signal gate, and so on. And for some problem, such as let's say the simulation of time or evolution of the wave function, we already have a general approach to construct a quantum circuit. But for general quantum, for general unit operators, construction of the quantum circuit corresponds to the general unit operators is usually very difficult for general cases. But for specific cases, we often know there are some guidelines to construct a quantum circuit.
Okay. Professor Bhupen Dev has a question.
Yes.
Okay. Yeah, he said he will ask the question. So, Professor Bhupen Dev, are you able to unmute yourself? Okay. He's unmuted himself, but I'm not able to hear him. Are you able to hear him?
No.
Oh,
I cannot hear.
Okay. Professor Bhupen Dev, we are not able to hear you. So in case we are not able to hear you, may I request you to please type your question in the chat box, then I can read out the question. In the meantime, does anyone else have any other question or questions?
Oh, I forgot to return the result of the quantum circuit simulation on IBM-Q.
Oh, sorry. It's okay. Yes.
Well, but unfortunately, it's still in Q. The simulation, the computation has not finished yet. Sorry.
Okay.
But anyway, the result is you can simulate by yourself by using this quantum circuit.
Yeah. Okay, so I didn't receive the question from Professor Bhupendev. Okay, are there any other questions? Okay, if not, then let's thank Professor Sugisaki for his wonderful lecture. Professor Bhupendev asked this question. So he asks, Alice makes measurements. She needs to send the results to Bob. Otherwise, Bob will not know what operations are to be made in order to get the original state. Are all information sent to Bob over the same channel?
So we need classical communication between Alice and Bob to recover the original quantum state. In order to recover the original quantum state in both sides. So all information sent to Bob over the same channel. Basically, only Alice has to do is tell about the measurement outcome of the her side, either 0 or 1 or 1 or 1 1. And Bob can recover the original state by using the information of the measurement outcome of Alice by applying this gates. So I don't know what the same channel means, but anyway, only need is the classical communication to tell about the measurement outcome.
Professor Bhupendev says that he's an experimentalist. So maybe in this case, then should we discuss this separately later, the question and the response to this? Would that be okay?
Yes.
Okay. Yeah, I'm just proposing this because there seems to be this audio problem. So then an exchange happens through text. So perhaps in view of this, we can then end the question and answer session for today's session.
Yes. And also,
okay.
The next lecture, this lecture here is usually scheduled on the Thursday, but next week the lecture will be in Wednesday, 17th, at the same time, 10 a.m. in India. Not yes, 17th, not the 18th.
Okay. Thank you for that note. Are there any other questions? Okay, if not, then let's thank Professor Sugisaki once again for a very wonderful lecture. So see you all in the next lecture. Thank you.
Thank you.